Good afternoon, everyone, and thank you for joining us for this webinar today. My name is Joanne from Rock Flow Dynamics Europe team. In case you missed our most recent webinars, this series we have invited some of our users to present their tNavigator projects to you. Today's guest speaker is Alex Thatcher, Petroleum Engineer at Oilfield Production Consultants. Alex is joining us today from London to present to you pressure rate deconvolution and its use in the reservoir simulation of the Corrib gas field. If you haven't joined one of our webinars before, just to let you know that all attendees today will be automatically muted. If you have any questions, please type them into the window in the control panel and we will address these at the end. Alex will be happy to answer some of your questions, and I also have my colleagues Alexandra and Maria from our technical support team on the line to answer any tNavigator related questions. We do usually receive quite a lot of questions, so if we don't answer yours live, we will follow up with you in the coming days. And we will be recording this session, so that will be uploaded to our YouTube channel along with all of our other webinars in due course. And if you have any other questions, feel free to reach out to us on asktnav@rfdyn.com. So for now, I would just like to say a big thank you to Alex and OPC for participating in this webinar, and I will now hand the controls over to you. Thank you, Alex.
Okay. Okay, hello, my name's Alex Thatcher. I'm a reservoir engineer for OPC. OPC are a global technical services consultancy to the petroleum industry. And the project I'm going to talk to you about is the latest development in pressure rate deconvolution and its use in the reservoir simulation of the Corrib gas field. So the project objectives. So the objectives were to use the latest development in pressure rate deconvolution as a history matching tool to improve our full field reservoir simulation model of the Corrib gas field. So to achieve this, the unit rate response function PU of the reservoir simulation model must overlay the unit rate response function of the historical data. Now, if you don't know what that means, don't worry, I'll get on to explaining that later. And B, to ensure the response functions overlap, the well completion and reservoir architecture of the reservoir simulation model must be adjusted by the usual parameters calculated from PTA, e.g. KH, total skin, connected volume, etc. So to do this, I added 4 high frequency build-ups to the full field reservoir simulation model, and I did it at the same time frequency as a standard well test, e.g. 1 second, 2 second, 10 second, 1 minute, etc. This is a bit ridiculous, but I wanted to push tNav to see how well it could replicate a proper well test. So before I go any further, OPC would like to thank the Corrib joint venture partners, Nephin Energy, Equinor, and Vermilion Energy for permission to present this material. So to give you a bit of background about the Corrib asset, so Corrib is a dry gas reservoir offshore the west of Ireland. It's currently the only producing field in Ireland. It's been developed with 6 subsea wells tied back to an onshore plant. It's a Sherwood sandstone reservoir with high net to gross but low porosity, low permeability system. The field came on stream in late 2015 and is currently producing off plateau, and the gas is treated onshore and exported into the Irish grid. So as again, Corrib is a joint venture between Nephin Energy, Equinor, and the operator is Vermilion Energy. So the relationship between Nephin Energy and OPC is that OPC provide regular technical support to Nephin Energy. So we do geological and reservoir studies, reservoir simulation, PTA, and operational monitoring on their behalf. So I only have time to talk about one well in this study. So for the case study, I'm going to show you P101Z. So P101Z is located towards the west of the field. It's a vertical well. It has a wellbore diameter of 6 inch. It's got 428 feet of perforations. The downhole gauge is located 1,000 meters above the perforations. And production started in late 2015, and the choke has been fully open since 2018. And every year we have a shut-in for maintenance for about 4 to 5 days, and the well is shut in at the surface. So you can see here we have the pressure data in blue, and we have the rate history in green. And using conventional PTA, looking at the derivatives, they all overlay quite well. So it's suggesting nothing's really changing within 100 hours. But we notice the distance from the derivative to the DP curve has been decreasing with time, and that's due to a rate-dependent skin. So now to get into pressure rate deconvolution and what is the latest development. So before I get into that, I just want to remind people of classical PTA. So here we have a variable rate history and we have a pressure buildup. And if we use the variable rate history and use superposition time on this buildup, we have a derivative that spans about 80 hours. So that's great for seeing the near wellbore characteristics. So let me get rid of the blue arrow. So what is pressure rate deconvolution trying to do? So here we're trying to convert this data into this. So what does deconvolution do? Deconvolution attempts to convert the observed variable rate pressure of a well into a constant rate pressure response of the same well. So you can see here from the beginning of production, we're trying to see what the drawdown would look like if we flowed this well at a constant rate for since 2015 to 2019. And why do we do this? Because if we take the derivative of that, we ended up with a derivative response that lasts the entire period of analysis. And in this case, it's around 5 years. And if we compare that to the conventional derivative, we've extended the derivative by 2.5 log cycles. That's 33,000 hours of data being added to the derivative. And that reveals much more about the reservoir architecture than what we see by monitoring a simple buildup. And you would never shut in the well for 33,000 hours anyway, it's not economical. So how do we do this? So let me get rid of that. So this all comes down to the convolution integral, which you can see here in the bottom left. And let me just explain all the terms in this equation. This equation's been around for a long time. So PT is the observed pressure data. So that's all your blue data recorded by your downhole gauge. Your PI is the initial pressure at the start of production. Again, that can come from the gauge or you could use it from MDT, whatever you think is the most accurate value of your initial pressure. Q here is your measured rate history in green at surface. And PU, so this is the important part of this equation. This is the unit rate response function. It's a signature of well and reservoir. And what is PU visually? PU is this DP curve here you can see on top. And if you take the derivative of PU, we have the derivative that spans, in our case, 33,000 hours. So how do we get PU? Well, pressure rate deconvolution in simple terms tries to use algorithms and condition PBUs to solve this equation for PU. But we find that it's messy and it often fails. So this is where I bring you to the latest development in pressure rate deconvolution. And in actual fact, it's not deconvolution at all, it's convolution. And this was developed by Michael Levitan. I'm not sure if you're aware of who he is, but he spent a lot of time developing the deconvolution algorithm with Mike Wilson in the PTA software Pi, but he found it's not robust enough. So he came up with an alternative idea. And that alternative idea is to manually reconstruct PU and solve for P. So here we draw the derivative unit rate response ourselves and we check the results of convolution. And he's invented his own software called Convex, Convolution Explorer. So just to give you a bit of background, Convex is for analysis of dynamic behavior of oil and gas reservoirs. It can be done on a single well or a multi-well basis, and it really extends PTA into the area of long-term production data analysis. And for the presentation I show you, I'm just going to make the approximation that this P101Z can be done on a single well analysis, because the idea of drainage area really works well on Corrib wells. So let me show you how we manually reconstruct PU. Okay, so on my screen on the top part of the slide, we have a conventional derivative in blue here. That's just to guide us, and I'll come on to that later. But here in red, we have the unit rate response function, and here we have the derivative. On the right-hand side in the blue data is the historical data. Again, that's recorded by the pressure gauge downhole. And in red, we have the result of convolution using this unit rate response function. And here we have to start somewhere. So here we just start assuming that we have infinite acting radial flow from the start, time t equals to 0, until present day, the end of the analysis period. And the distance between the two that defines the skin, but I have to start somewhere. And you can quite clearly see that the results of convolution with this unit rate response function is incorrect. There's obviously a lot more depletion going on in the system. So our first step is to interactively draw the derivative of the unit rate response function. And we are guided by the 2019 build-up, but that ends after about 100 hours. So the question is, what happens after 100 hours? So again, if we apply convolution on the unit rate response function, we can see there's clearly not enough depletion. So we can't say that infinite acting radial flow continues after the build-up. So now we can investigate what might happen after the end of the 100-hour build-up. So here I draw a half slope and then a unit slope just by drawing whatever I want. But you can see here I'm constraining it with 33,000 hours of data, and it's still not correct. It's clearly not correct. The flowing pressures are off and the build-up pressures are off. Eventually, very quickly, I end up with this response function here, and you can see that it matches my build-ups fairly well, and it matches the flowing pressures fairly well as well. So we are really constrained in the first 100 hours of the build-up by using a standard derivative, but then to constrain the late time data, we constrain it with 33,000 hours in our case. And we do this until we get an acceptable match, and here I think it's quite acceptable. So again, why did we do this? So it allows us to analyze this derivative using standard PTA equations. Remember, PTA came from the first assumptions was from a well flowing at a constant rate from the beginning of time. So there's no different PTA equations going on here. We've just gone back to basics. So let's have a look at more detail about what we can see in this. Well, we have wellbore storage, we have radial flow, we have a slight downturn in the derivative, increasing maybe a greater KH further away from the well. After about 100 hours, we see boundaries / a change in mobility / sterility. So you see the upturn. And then eventually it manifests itself into a unit slope. Now this is a drawdown response. So once you reach the limits of the reservoir, you will begin to see a unit slope. So again, here we can calculate our KH and decouple to our K. We get our total skin, and we get our unit slope and some information about the architecture. I'll start down here. So as I said, that P101Z has a lot of rate dependent skin. So analyzing this over time shows that my mechanical skin is +2 and my non-Darcy skin is 1.19 times 10⁻⁴ days per 1,000 scuffs. Analysis of the reservoir architecture using standard PTA shows that my connected JIP would be about 155 BCF, and doing some quick PTA modeling shows that my reservoir geometry is more elongated like this rather than just a simple box around P101Z. So that's the deconvolution part of it. So now I'm going to take you on to how I used this as a history matching parameter in the full field reservoir simulation model. So just to give you a bit of background, so OPC working on behalf of Nephin Energy were focusing on an update of the existing Corrib numerical simulation model. And the objective was to incorporate the results of the extensive PTA work that we complete yearly on Corrib and create a framework for history matching. Again, I only focus on one well here. So let's have a quick look at the model. So we've got 6 wells. This model originally has well PI multipliers. There's many faults in a northeast-southwest orientation. It's 2.6 million cells, including upscaling. And without the high frequency buildup runs, it was 100 minutes. and that was about just over 1,000 time steps. But with the high frequency buildups, the time steps went to over 6,000, and it actually only took 5 hours to run, which I know you're saying is a bit long, but I was really pushing tNav to the limits. So if we look at the previous history match, when we look at the data plot and zoom in on the 2018 buildup, we can see that the connected volume is far too large. That's quite clear. But when we look at the data plot, the flowing pressure, well, you don't know if it's because the permeability is too high, maybe the skin is not high enough, or is the mismatch in the flowing pressure due to the connected volume. And that's why we use PTA and derivatives to be able to decouple all of these things. So just to give you an overview of the workflow of my project and how I integrated convex in tNavigator. So I run the numerical simulation model in tNavigator. I export the results to convex and apply reconstruction of the unit rate response on the simulation results. I then analyze the response functions using standard PTA techniques. And then I ask myself, does the response function of the simulation model match that of the response function of the historical data? If it's a yes, a match is found and I can stop. If it's a no, I need to figure out why there's a mismatch. I need to go back, update the ResSim model and repeat the process. So just so you can visualize it, here I have a response reconstruction of the historical data in black and the ResSim model in red at the start of the process, and you can see there's a mismatch. I'll get onto that later. And by the end of the process, we want the red and the black to overlay quite nicely. So I'm going to show you how I did that. So using the old reservoir simulation run that I showed you on the previous slide, I exported the results into convex and I applied response function reconstruction. And I ended up with this red line. And to prove that this is the response function of the old ResSim model, we can check the match here. So blue is the simulation results. It's not the historical data. And what we're showing is we can replicate the reservoir simulation using the reconstructed response function. And at first, if you see this, well, it looks like the radial flow is too high, the derivative is too low, and the skin is too high. The unit slope looks similar, and that's a function of a log-log plot. So a log-log plot magnifies the early time data and compresses the late time data. So although it looks similar, when we actually analyze this in PTA, what we find is the connected JIP is 10% too high. It's 171 when it should be 155 from our PTA analysis of historical data. And what we also find was the KH was 73% too high. And using well PI multipliers, the total skin is now plus 17.6 and it should have been plus 5.7. So basically what's happened is there wasn't enough pressure loss due to Darcy's law, and to try and fix that using well PI multipliers, they ended up putting too much skin on. But as you saw on the previous slides, it still wasn't enough skin to actually get the flowing pressures to match. Yeah, and just on the PI multipliers, it's really not advised to use well PI multipliers when you've got high rate dependent skin, because the PI of the well is changing daily as the rate decreases. So what I wanted to do was remove well PI multipliers from the model. So now I will start to show my history matching that I did. So what I did was I removed the well PI multipliers. I added a mechanical skin of +2. I entered the PTA D factor using the keyword WDFAC, and I drew a box about 3,000 foot square around P101Z, and I reduced the permeability in the XYZ direction. What I find is I managed to shift the, so then I ran the simulation, I exported to convex, and I reconstructed the unit rate response. And what I found was I managed to shift the mobility up, but the surprising thing is my total skin was wrong. So when I analyzed the skin over time, my output skin didn't match my input skin. So when I ran it on the simulation model, I applied PTA analysis. I found that my mechanical skin was minus 0.1, but I input it as +2. And likewise, the D factor was wrong. Now there's two ways to get around this. So the first way, which is the quick way, is to use a sort of upscaled skin. So instead of inputting a +2 skin, I found that if I input a +4.8 mechanical skin, I can shift this blue line up. And likewise, I have to increase the D factor by 45%. But this is all right, but it's not a great method, because what if my boss says, well, what can we do to remove the skin and how does that affect the forecast? I'd rather be using the correct skins as an input and output. So what I ended up doing was I added in an LGR, because this was a gridding effect. So here you can see my previous cell sizes were about 30 to 40 meters. And then I ended up putting a massive LGR in just to see how tNav again would cope, pushing it to the limit. So the cell sizes are now about 1.3 meters. But unfortunately, the runtime increased to 15 hours. But again, running it, taking it into convex, applying unit rate response function reconstruction, you can see now my skin was modeled correctly. And my derivative is matched fairly well. And you can see here now I've managed to shift the blue line up to the green line, which overlays the PTA of where it should be. So I've not touched the connected volume yet, so that's next. So basically for connected volume, what I did was just the same way most people would, using pore volume multipliers. So what I really want to talk about is a cool feature in tNav, and it's based on the streamlines that you get. So here in purple, you can see the streamlines of P101Z on the left there. And if you take that into 3D and apply the drainage area cut and set the property to pore volume, you can see the shape of the drainage area, which is what I thought was quite cool. And that worked well with the PTA model. If you remember, it showed it's quite elongated, and that works quite well with the geology because we have many faults in this direction, and we also have some dynamic boundaries as well. So what I thought I would find is that the pore volume of this cut, after fixing it, would equal the pore volume of PTA. And what I found was this property was a function of the streamline density, which is set by the user. So when you have a streamline density of 1, the connected JIP was 163, and it should have been 155. So after speaking to tNav, we agreed that connected volume drainage cut is a great tool for visualization, but should not be used quantitatively, as tNav is not a streamline simulator. But to get the 155, I had to set the streamline density to 1.3, which is not far away from 1. But it shouldn't be used as an absolute. So after fixing the connected pore volume, you can see the late time unit slope now overlay exactly, and I have a good match over everything. And if we look at the variable rate history again from 10,000 hours onwards, and if we zoom into the 2018 build-up, you can see that now my ResSim model is going through the build-up exactly. I have the connected volume over time modeled correctly, and my well flowing pressure is also modeled correctly. So some challenges and useful features. So the simulation times was a big challenge. You know, it went from 90 minutes to 5 hours with increased time steps. But that, again, that was pushing tNav to the limit. I really don't need that many time steps to do this workflow. So that's an area of improvement I can do in the future. Again, running the simulation time from 5 to 15 hours with the addition of the LGR. Again, it was a bit of a ridiculous LGR. That can definitely be optimized. And I tried this simulation on different reservoir simulation software, but it needed a few days to complete. Therefore, this workflow wasn't really viable with the LGRs and the very detailed time steps. Another challenge I had was replicating PTA skins. So again, it was found that with large grid cells, pressure drops due to skin derived from PTA could not be replicated. And an extremely refined LGR, where the size of the grid cell was almost approaching the well diameter, greatly increases the runtime. There is a solution to this, as I mentioned, that you could use a sort of pseudo skin or upscaled skin and D factor to overcome this, but that also has limitations. Visualizing drainage areas, again, as you saw on the previous slides, it was an extremely useful feature. You know, my PTA and my ResSim was talking to each other with the shapes of the drainage areas, but caution is advised, as this is a function of streamline density, so you need to be careful. So going back to the simulation time, so I told tNav about my problems, and I asked them what they could do about it. So they tried, one node is like running it on my workstation in the office, and 10 nodes is like running it on a lot more workstations. And you actually find that tNav managed to take it from 15 hours down to 3 to 4 hours. And especially if I, decrease the time steps to something more practical, and I consider optimizing my LGR or using pseudoskins, I could definitely get this simulation time down to maybe, even 1 or 2 hours. But going through the process of exporting the data to convex is actually very fast, and it tells you exactly what's wrong. And for the case of P101Z, exactly what's wrong with my simulation model. So project summary, so comparing response functions between the simulation model and historical data can greatly improve / speed up the history matching process, as it provides a fingerprint of the well in the form of a Bourdet derivative. This approach typically highlights the reasons for the mismatch between the actual data and the reservoir simulation model. In the simple case for P101Z, I found out that the permeability model was too high, the well productivity was too low, that's because of the wrong skin model, and the connected volume was too high, and an improved match was quickly found. Using the workflow proposed will greatly aid the history matching of the other more complicated wells in the Corrib Gas field, where the unit rate response function is not so simple as P101Z. And again, using tNav provided a high-speed simulation tool that allowed OPC to look at the integration of PTA into the full field simulation model, and provided some useful additional features to analyze the results. So the value of this project, so improved reservoir understanding through the use of a Bourdet derivative that spans 33,000 hours instead of 100 hours in a single build-up. Full integration of the PTA dataset / improved interpretation into the reservoir simulation model. This could also be used in products like material balance, IPR generation, and of course for PTA itself to make PTA models. It also provided a quick way to history match the simulation model whilst maximizing the use of PTA data. And at the end of the day, it's given us increased confidence in the ResSim model, thereby improving business decisions for Nephin Energy and the Corrib joint venture partners. So thank you for listening. I would just like to thank the joint venture, RFD, and Michael Levitan at Convex for allowing to share my study. If you've got any questions regarding Convex or require any subsurface help, contact OPC, myself, or Michael Levitan. And I just want to share some SPE papers that I definitely recommend reading. A few of them are about deconvolution by Levitan, and there's also a few papers from Rockflow Dynamics more about the simulation software itself.
Thank you very much, Alex. Oh, thank you for sharing the project with us and for a brilliant presentation. I think Alex and Alexandra and Maria are just having a look through some of the questions, and they'll have those over to you. We do have quite a lot coming in, so as I said earlier, we'll make sure we follow up with anyone via email if we don't have time to answer your question live. Just to let everyone know as well, the last webinar in this series will be next Thursday at the same time, and that is a presentation by Cairn Energy, so make sure you join us for that. Alex, can you see some of the questions that have come in?
Yeah, so I have a question here. Do you think that this could be applied in other fields, or was there something special about Corrib that made it work? Yes, we have applied this technique on other fields. The question is, does your data set work with deconvolution convolution? There may be cases where your entire data set is not consistent with convolution. However, that's why Levitan calls the software a Convolution Explorer. So you're trying to explore the data set and try and find areas of the data that work with convolution, and what can you extract from that data into something meaningful. And one of the SPE papers I suggest down here is Levitan and Noble Energy and the big gas fields. I think it's offshore Israel, and he shows that Convex didn't work on the whole data set, but he managed to extract some very meaningful results. One of those was which wells were getting support from an aquifer via edgewater or from underneath. And that's going to help Chevron now develop that field further for water injection, etc. So is tNav user-friendly enough to make this PTA simulation iteration easy, or did you have to spend lots of time getting data into tNav? No, I thought it was very easy. It's extremely easy. I'm not an experienced reservoir simulation engineer, but I managed to do this project very fast. And, I could export the data from the graphical pane, copy paste it direct into the PTA software. The integration of taking it from tNav to convex, it only takes about 10 minutes or something, even to reconstruct the unit rate response function and apply PTA on it.
I have one more question, Alex, before we wrap up.
Yeah, I got one here. I can already get KH and skin from normal PTA, so why do this? So convex is not here to replace conventional PTA. It's here to supplement it. And it's bringing PTA into the long-term surveillance area of analysis. If anything, it's competing with what you would call rate transient analysis, but doing it on the PTA scale. So that becomes very valuable. But for instance, for the simple case of P101Z, yes, I got KH and skin after 1 hour. But for instance, if you have a horizontal well where you don't get the pseudo-radial flow till very late time, you might be able to shorten your times of shut-ins and extract the unit rate response function, which might show you the late time radial flow regime, but you didn't have to do that at cost of shutting in the well for hundreds of hours. And that's really going to help you with your modeling work.
So thank you very much for answering those questions. We will finish up there because we're coming out of time anyway. So thank you very much again, Alex, for preparing the presentation and presenting it to our audience. It's greatly appreciated. And we hope to see everyone on the next webinar next week. Thank you very much.
Okay, thank you.